Welcome to the Cosmic Savannah with Dr. Jacinta Delhaize
and Dr. Daniel Kahneman. Each episode, we'll be giving you a behind-the-scenes look at world-class astronomy and astrophysics happening under African skies.
Let us introduce you to the people involved, the technology we use, the exciting work we do, and the fascinating discoveries we make.
Sit back and relax as we take you on a safari through the skies.
Hi and welcome to episode 45. Today we are talking all about the James Webb Space Telescope.
So we're actually going into the skies this time.
Yes, Dan spoke with Professor Christy Tremonti from the University of Wisconsin-Madison.
Yeah, so I had a fascinating discussion with Christy. She is a professor, as you said, in the US, the University of Wisconsin-Madison, which is a SALT partner. So we've spoken about the Southern African Large Telescope, SALT, many times now. And that is an international telescope owned in large part by South Africa, 50%, but then owned by various institutions around the world as well. And the University of Wisconsin-Madison is one of them. So Christy Tremonti works on galaxy evolution. She's an observational astronomer, so she looks at galaxies through telescopes, and she does a lot of her work using space telescopes. So she's worked with SALT, obviously, but she also has worked the Hubble Space Telescope for many years, and she will be working on the James Webb Space Telescope.
And the James Webb Space Telescope, of course, is a really big deal. This is a telescope that's been in construction and planning and preparation for, gosh, how many years now?
Oh, I think decades. I think it was first conceived when Hubble launched, which was 1990. So
Right, and it's kind of been sold as the kind of new Hubble, the replacement for Hubble, but it's actually not, as we'll hear from Christy later on. It's actually kind of a bit of a different telescope, but yeah, still a space telescope. And if you would like to know a bit more about space telescopes, you can listen to episode 17, where we spoke to Dr. Stephen Crawford about the James Webb Space Telescope, JWST for short, and also to Jayan Crawford, who was telling us how they make the beautiful images from the Hubble telescope that are so famous and that many of you probably will have seen.
So yeah, it'll be launching on the 18th of December 2021, and it is a huge telescope. It's about 6.5 tons. It has a mirror which is 6.5 meters across, and it will be folded up, well, it's already folded up, like a sort of butterfly inside a cocoon, launched into space, and then it'll have to very carefully unfold the mirror, unfold all of the instrumentation into this massive beast, which is going to sit up in space.
Yeah, that's just unbelievable. I can't believe they're actually going to do this. This is just such an amazing feat of engineering and science. And I know I've mentioned this on the podcast before, but I'll say it again because it's amazing. I've actually seen the JWST being constructed at NASA Goddard, and I think it was 2016 I went there, and there's like a viewing platform, and it just so happened that they'd opened up the mirror and it was facing the viewing platform at the time, and it was amazing. It's this big segmented mirror, and it's gold-plated beryllium. And so you basically see your reflection very accurately in gold, and it was really incredible, and it's huge. This thing, just like, how big did you say the mirror is? Six meters or so?
6.5 meters.
Yeah, which you might not think is a lot, but that actually is enormous. And to think that this whole huge bulky thing is going to go very far out into space, open a solar shield, and then open the mirror. It's nerve-wracking. Like, what if it goes wrong? Like, astronauts can't get there to fix it, so...
Yeah, I think that is a point. And I guess that's why it's so stressful, because firstly, you're strapping it to a rocket, but then this elaborate unfolding thing has to happen. You know that they've built in various fail-safes, but still, it's a very, very scary day. And after a lot of planning and research and construction, engineering, going to be a pretty exciting day. I'll be watching it live. I can only hope that they have coverage half as good as SpaceX does.
Yeah.
But I can't promise that. And and then I think that then it's underway, and we wait the few months which it'll take to unfold into a beautiful butterfly.
Christy is going to tell us about her plans to use the JWST to study the life cycles of galaxies and feedback and from stellar explosions and from black holes and these sorts of things. And this is something that we spoke with Dr. Moses Mahotzi about in episode 34, and how he uses the SALT spectrograph to do these sorts of stuff. And this is similar science to what Christy will be speaking about. So if you'd like to know more about that science topic, you can check out episode 34.
Christy will explain it in more detail, but it's probably important to note that the James Webb Space Telescope has slightly different science goals to something like Hubble. Works in different wavelengths, and it can look at different science problems. So it's going to try and solve some mysteries which we haven't been able to delve into. And one of the highlights that they are hoping to see some of the first stars, which is really quite exciting.
Excellent. So without further ado, let's hear from Professor Christy Tremonti.
So today we're joined by Professor Christy Tremonti, who is a professor in the astronomy department at the University of Wisconsin in Madison in the USA. Christy, welcome to the Cosmic Savannah.
Thank you so much. It's a great pleasure to be here.
Thanks for taking the time to chat to us. Maybe just to start off with the listeners, can you just give a little bit of a background as to who you are, what you work on?
Sure. So I've been a professor here for about 10 years, and my main field of study is galaxy feedback. So it's this process by which, stars and sometimes black holes return a lot of energy to the surrounding gas in a galaxy. And sometimes it can actually explosively and violently blow this gas right out of the galaxy. And this process, it turns out, has a pretty big effect on galaxy evolution.
So we're talking about supernova feedback, or are there other mechanisms which are underway here?
Yeah, so it's a lot of the energy for this process comes from these supernova explosions, so a massive star exploding. But it turns out even before these massive stars explode, they're kind of driving winds into their environment right off the surface of the star, and that can be important too. And then, black holes can also contribute. The supermassive black holes at the centers of galaxies can also contribute to this process.
So you're an observational astronomer, which means you use telescopes to look at these things. How do we observe winds in galaxies?
Yeah, this is a great question. It's been historically really tricky. So a nearby galaxy that is in the northern hemisphere, so maybe not visible to most of you, is M82. And this is a starburst galaxy that's the closest starburst galaxy to us. And we say starburst just meaning it's having an unusually high rate of star formation. And therefore, there's a lot of this feedback happening because we have a lot of hot, young, massive stars. In that galaxy, we can take images in the light of ionized hydrogen, and we actually see, these sort of bipolar, not really jets, but bipolar kind of cones of material coming off the galaxy. And when people first took images of this galaxy, back in the I think 50s and 60s, they literally thought the galaxy was exploding because it looks like that. But that's a really nearby case, and there aren't many galaxies where we can do that because this material is very faint and hard to observe. So it's more typical for us to use spectroscopy. So we're taking the light, we're splitting it up into its component, wavelengths or colors, and we're actually looking for absorption features from particular atoms or other electronic transitions. I guess we're going to take advantage of this thing we call the Doppler shift, where if some gas is moving, we would see its wavelength shifted relative to where we expect. And so by measuring those shifts, we can tell how fast the gas is moving.
All right, so we've spoken about spectroscopy before, and basically, as you said, we're splitting up light into its constituent wavelengths, and from that we can learn what the gas is made up of. We can learn about how fast it's moving, whether it's moving towards or away from us. We've spoken about this before with SALT, the Southern African Large Telescope, which is based here in South Africa. And I know that the University of Wisconsin is a partner on SALT. Have you used SALT before in your work?
Yeah, in fact, a student of mine is just getting ready to resubmit a paper that he wrote using SALT spectra. So one of the things SALT is really great at doing is looking at very blue wavelengths, which are traditionally pretty hard to look at from the ground. but the spectrograph on SALT is really sensitive to these bluer wavelengths. And in this particular case, we're looking at an object that is very mysterious because it has a supermassive black hole in the center, but that black hole is really highly obscured by dust. So dust absorbs a lot of starlight, and this galaxy gets classified as an extremely red quasar. So quasar just means it's a supermassive black hole that's accreting at a really high rate. But this one's buried in dust, and we're trying to figure out what's going on with it and why it has such, interesting spectra. The spectrum of this one's really unusual.
You mentioned this is very difficult from ground-based telescopes. I know you've worked previously on the Hubble Space Telescope. Is this something that Hubble does? Does Hubble have a spectrometer on it?
Yeah, so Hubble has the cosmic origins spectrograph works in the far ultraviolet. So in this case, the feature that I'm looking at is, not quite that blue. It's still within what we'd call the optical wavelengths. But if we want to look at other, features especially in nearby galaxies, it's hard to do any other way than going to space if we want to look at the ultraviolet. And it's been super important for studying very faint gas around galaxies that we can only typically see using these absorption line spectroscopy techniques.
We've spoken about Hubble previously on the podcast, where we spoke to somebody who had been working on the beautiful images which have completely spoilt us for the last 30 years of Hubble being up in space, and trying to sort of really show what gas that was and properly colorize these images. I mean, I think we've been completely spoiled, but I imagine from your point of view and the discoveries that have been made over the past 30 years, Hubble has really been a real workhorse and something quite spectacular for the field.
Yeah, absolutely. I mean, it's been just a complete game changer in terms of what we know about galaxies. And I think with the next generation telescope coming online soon, the James Webb Space Telescope, we're going to see just another huge increment in what we know about galaxies and their evolution. It's going to be, just a complete game changer.
Well, that's it. And I really did want to talk to you about the James Webb Space Telescope, because I think we all have this feeling, and I certainly have it myself, that this is going to be a game changer, but I just don't know how. And maybe nobody does. We talk a lot about the SKA here, the Square Kilometer Array, which is coming, and there's a lot of talk about the unknown unknowns, that the telescope's going to be so powerful, we'll discover things we weren't out there looking for. So just for the listeners, the James Webb Space Telescope is much bigger than Hubble. It's a 6.5 meter mirror, and it will be launched on the 18th of December, hopefully. And that's very exciting. And you've been working on it, or you will be working on it?
So, astronomers apply for telescope time. So we write these proposals and they're all peer reviewed. So you get a big group of astronomers together and they try to pick the proposals that they think are most exciting out of a very big pool. And so I was fortunate enough to have some time that, probably we won't get data for maybe a year or so, because it will take, this telescope is really unusual. Once it launches, it's got to go all the way out to L2, which is pretty far away. So it has to get there. And then unlike Hubble, it has to kind of unpack itself. So when Hubble was launched, we had astronauts, who were right there, who could set things up, right? But in this case, the telescope has to literally unpack itself. And that's a pretty lengthy process that has to be done, really slowly and with tremendous care, because we can't go and fetch it back if anything fails. So that process will take a while.
So what is L2?
So this is a Lagrange point, which is kind of a stable point between, so it has to do with, the Earth orbiting the sun and the moon orbiting the Earth. And L2 is kind of this stable point where we can sort of park telescopes and they will stay there. And it's just sort of like a balance point between the gravity of these things.
But basically, the James Webb Space Telescope won't be orbiting the Earth as we think of, most satellites or the International Space Station, or as Hubble did, sending this out way further. And it kind of sits in this space, and I can look up how many kilometers exactly it is away. But it's essentially orbiting the sun, right? And interacting with Earth and the moon too. So it's not coming back to us. This unfolding of a telescope on the way to L2, it causes me extreme anxiety. I don't know how you feel about it, but every time I look at it, it's absolutely terrifying. They're folding this telescope up like a butterfly in a cocoon, launching it into space, and then hoping it unfolds perfectly.
Yeah, it is kind of terrifying, but I have a tremendous amount of faith in the people who design these things. I think, in fact, I was reading somewhere that, some of the folding of the sun shield, they have to pack this giant sun shield very tightly in there, use techniques developed for origami to get this really optimal fold. So it's kind of amazing.
I imagine absolutely everything has to be optimized. So,
Yeah, it really, really does.
and it's going to be a very anxious day too. I mean, the 18th of December is strapping this thing to a rocket, but
Yeah. So there's launch, and then, I think we'll have sort of more like 6 months to hold our breath while the whole thing slowly gets out there and starts to, unfold itself and turn systems on one by one. And it also has to cool down a lot. So that's part of the process too.
yeah, I mean, I must say that we watched the Perseverance rover land earlier this year, and the things that we can pull off now across the vast distance of space, I think we can be fairly confident we pulled this one off. But still, it's a lot of effort and a very, very big telescope. So let's talk about that telescope then. So Hubble was launched 30 years ago, 30 in 1990, right? And it's still functional and still one of the best telescopes we have. 30 years worth of technological improvements. What are we looking at here?
Yeah, that's a great question. One remarkable thing though is Hubble's still pretty state of the art. Like when we talk about proposal over pressure, how many people are proposing relative to how many got time. I think it's still like only 1 out of 9 proposals gets time on the telescope. And part of that is because we've had the ability to send astronauts up to service it and refresh those instruments. But it is, because we have James WST, we're not going to suddenly stop using Hubble. I think it'll be amazing to have both of them together. James Webb is one thing to remember is it's not just a bigger Hubble, it's trying to do something kind of more fundamentally different. And that's primarily because it works at near and mid infrared wavelengths. So these are wavelengths that are longer than our eyes can see. And Hubble edged just a little bit into the near infrared, but the telescope wasn't optimized to work at those wavelengths. And everything about JWST has been designed to take us into this new wavelength regime. We have had smaller, orbiting observatories like Spitzer that looked at these wavelengths, but they were just much smaller telescopes that didn't have the kind of resolution that James Webb will have. So I think that's the thing that astronomers are super excited about.
So we're going to be able to see things. Obviously, we'll be able to see things further than we've ever seen them before. But we're looking in a wavelength and a resolution which we haven't really had access to before. And then in terms of the science case for this, what are we looking for? So you work on galaxies and galaxy evolution, and there's going to be a lot of work on galaxy evolution. What are you hoping for from James Webb, and maybe what are your proposals?
I mean, the telescope's going to do a wide array of science. So, galaxy science is just a chunk of what it can do. And one of the ironies is, James Webb has been in the planning process for a long time. It was really around sort of, I think even before 2000, that people were starting to plan the telescope. And astronomy changes really rapidly. So at the time it was designed, extrasolar planets were not even a thing. They were sort of a few little discoveries had been made, but it just wasn't a big scientific field. And now exoplanet science is going to be a large fraction of what the James Webb Space Telescope does. But it turns out, some of the choices they made that were designed around distant galaxies worked well for extrasolar planets too. I don't work on that field, so I won't say too much about what they're trying to do. And it may be fun to get, another guest who does. But for galaxy science, the big thing is trying to push to higher redshifts, which for us, redshift is just a measure essentially of a galaxy's distance from us. And our universe is expanding. And because of that, the light, as it travels towards us, the wavelengths of light also get stretched out. So when we see galaxies that have these very stretched out wavelengths of light, we know that they must be very distant. And remarkably, when we look at distant objects, we are actually looking back in time. So, like when you look at the sun, you're not seeing the sun as it is right now. You're seeing the sun as it was 8 minutes ago when light left the sun and started traveling towards your eyes. When we talk about a kind of nearby galaxy, a nearby galaxy might be billions of light years away, meaning it has taken light a billion years to reach us. So we're seeing that galaxy not as it is now, but as it was a billion years ago. When we look at the most distant objects that we can discover, we can look back and actually watch our universe evolve, which is something that we can't do in any other field. So this ability to look back in time is really huge and super exciting for JWST.
Yeah, and of course we can't look at the same galaxies over time, but we get a snapshot of the universe as it was at each of these times in the past. And James Webb being such a big mirror and such a sensitive instrument, I presume it's going to be able to look back right to the very beginning of the first galaxies. Or is that the goal, right?
Yeah, so that's certainly the goal. We want to see those very first galaxies in formation. And, those first galaxies are really small, which means, they're not going to be very luminous because they don't have a lot of stars yet. Also, they're very distant. So distant objects are always fainter. So that makes it really hard. And the light from those galaxies is going to be redshifted to really long wavelengths. And that's the reason we need a telescope that's optimized for the kind of mid infrared if we want to see those very first galaxies. And so, we think of the Big Bang as the beginning of our universe. And we know some of these galaxies were already, forming and in place a billion years after the Big Bang. We hope to look back, even a little bit further than that and really see those, maybe even evidence of the very first supernova happening. It's just going to be very exciting to get a view of those things.
You said we're going to have to wait a year, and then I suppose we're going to have to wait even longer for everything to be processed and the papers to come out. But certainly in the next 5 or 10 years, we can expect some pretty spectacular stuff coming out of JWST.
Yeah, and we may see some results sooner than a year, I would guess. Some of these things are so new that you don't have to spend ages digging into the details. You're sort of, we call it skimming the cream. Yeah. There's some really great stuff. So
do you think they're going to do a sort of a calendar shoot, a first couple, just some spectacular public outreach shots for us?
Yeah, actually, I don't know whether there's public outreach shots, but what they did that I thought was a really great idea is they had proposals for early release science. So they had teams, all over the world. Anybody could submit a proposal, but it was a little different than the normal proposal process because you had to, you're sort of proposing for a science demonstration image rather than doing, a big survey. You're saying, I'm going to show that we can observe gravitationally lensed galaxies and get something incredible back. And I'm observing this one object, but the data goes public to everyone, I think, at the same time. So you're kind of giving up on, normally we get to keep our data to ourselves for 6 months to a year. So you had to give up on the proprietary period, but you would be one of the first people to get your object observed. And so they picked these kind of demonstration cases from many different fields of science in order to get real data in the hands of astronomers right away. So one of the concerns with the telescope is because it works at these long wavelengths, we need to keep the telescope very cold because things that are hot also kind of radiate at these long infrared wavelengths. And we don't want radiation from the telescope contaminating what we can measure from the universe. So the telescope has to be cooled down to incredibly low temperatures. And I think we use liquid helium to cool it. But that means there's a consumable. It will run out. We can't, operate JWST for 30 years like we operated Hubble. So there's a real urge to be as efficient as we can and help people get data and plan their observations right away.
What is the lifespan?
So it's nominally 5 years, but there's a lot that they don't know. So I think we can confidently expect 5 years. I think there's a lot of uncertainty in that number, whether they might be able to stretch it to 10. Just a lot of it will depend on how the telescope reacts thermally in its environment at L2. And a lot of things they can't know until they get there and see how things function. But the Hubble engineers are incredible. I mean, they have done amazing things with Hubble. Like, we use gyroscopes to stabilize the telescope and to be able to point it. And Hubble has lost a lot of gyroscopes. They've stopped working, but through just incredible feats of engineering, they have been able to operate the telescope almost as well as it operated before, with no real difference to the scientists, with a very small number of gyroscopes. So I don't underestimate the cleverness of the people who work on these instruments.
Well, let's hope we don't have to push them too hard and everything just works. They can
Yes.
get a couple of months off before anything breaks.
Definitely.
And for your particular research, you've put in a proposal to do something on the outflows, or?
Yeah, so I'm studying this set of galaxies that are interesting because they're not super distant objects. They are sort of 7 or 8 billion years old. They're not sort of 13 billion years old like the ones we'll try to look at with the James Webb Space Telescope. But they are in many ways like some of the distant galaxies in that they have very high rates of star formation, and they're very kind of compact. And we think that they're the result of a merger between two galaxies that drove a lot of gas right into the center of the new galaxy. And we see just incredible outflows from these objects. They have just much higher, much faster outflows than most other star forming galaxies. And we think it's because their star formation is happening in such a kind of compact configuration that you're kind of more able to capture all the energy from those supernovae and use it efficiently to drive outflows. But a perennial question with our work has always been, well, how do you know it's star formation and not a supermassive black hole that's driving these outflows? And we use the Chandra Space Telescope, which looks in X-ray wavelengths, and X-rays are often produced by supermassive black holes. And we could say, well, we don't really detect these in Chandra, but a possibility is that that black hole is just super buried in this dust, this stuff that absorbs light. And if it's super buried in dust, we would not see it in X-rays. We wouldn't see it in the kind of visible light that our eyes can detect. But it would come out at these, mid-infrared wavelengths where JWST is super optimized to work. So we're taking mid-infrared spectra of our galaxies, and I feel like we've been wrestling with this question, like, are supermassive black holes driving the outflows for a decade? And it will be so great to finally have this question answered. So I'm super excited to get the data.
And JWST is just going to cut right through that dust, right?
Yeah, so we will see all kinds of, and so this mid-infrared region is just incredibly rich in all these spectral features. So we have a variety of atoms and molecules that emit light. Even if we find out there's no supermassive black hole there, which is our expectation, but we'll see, we'll get an incredible amount of data just on the conditions of that starburst from looking at that sort of, we're actually seeing the dust glowing when we look in these mid-infrared wavelengths.
I mean, I'm looking forward to it. I think that we'll have to speak to you again in a year or two's time and hear what you found. I think that there's going to be JWST science queued up.
Yes, for sure. Absolutely.
Thank you so much for speaking to us today. I think it's very, very exciting. The launch is very exciting, and I think that the science even more so. And is there anything else you'd like to share, or anything else you're excited about?
Yeah, I think, again, just stay tuned for those very first galaxies. It's not really what I work on specifically, but I'm super excited to see what we will learn about the very earliest stages of galaxy formation. I think that's going to be just where we see the very real revolution and a lot of important questions answered.
And the NASA calendar 2023 is going to be stunning, right?
Yes, absolutely.
Christy, thanks again for joining us, and we'll chat again soon.
Thank you so much.
Thanks for that, Dan. A super interesting discussion there with Christy. I wanted to talk about Lagrange too for a second. This is something that I've been wondering about for a while because I hear when we're talking about space telescopes these Lagrangian points, and I've never actually bothered to go and find out exactly what it is. And so when Christy was speaking, I was interested, and so I Googled it, and it is basically a point in space between two massive objects where you have this kind of point of gravitational balance. So in this case, you've got the sun and you've got the earth going around it, and usually something that is further out in an orbit from the earth compared to the sun, orbit at the same speed as the earth, but because it's on a larger radius of orbit, it will fall behind the earth in its orbit path. And so this Lagrangian point is interesting, L2, because it is further away from the sun than the earth, but any object that is at that point will orbit the sun at the same
So it's not the same speed because it's further out, right?
Yeah.
So for the older...
What word am I looking for, Dan?
For the older listeners, you might remember an LP, or for the younger listeners who go back in vinyl, I think there's just a small period of listeners who...
I have a vinyl player.
Exactly. There's a small period of listeners who in between who didn't know about vinyl, just had DVDs. Anyway, so you can see the record is going around at the same rate, but the outside obviously has to go faster than the inside because it's covering a larger distance. And it's kind of the same with this. So you have the spacecraft completing a larger orbit in the same time as Earth. So it's moving faster, but it stays the same position relative to the Earth and Sun, right? It's in a straight line between Sun, Earth, telescope.
That makes sense. That was a good analogy. Well done, Dan. You saved me there. So the Earth and the satellite JWST will orbit the sun at the same rate, and so JWST will stay at the same position relative to the Earth at all times.
And that means we don't have to worry about it getting too far away. But still, it's very far away, and it means it doesn't have to worry about any sort of interactions with the Earth, or it doesn't have to worry about day or night.
Yeah, exactly. It's actually 1.5 million kilometers away from the Earth, which is a lot. And to put that into context, that is 1% the distance between the Earth and the Sun. So 1% of that distance, then add that onto the distance from the Earth to the Sun, and then that's where the L2 point is.
I asked Christy if they were gonna take some beautiful calendar shots when they turned the thing on, and I'm sure they will. But what I didn't ask her, and I just thought about now, is whether they're gonna take a shot of the pale blue dot.
Oh, yeah.
Hey, right? Like with that telescope, I mean, it won't be a pale blue dot with that telescope. They'll probably be able to read your watch. But, like it's like, yeah, I mean, I wonder if they're going to look back on Earth.
Yeah, that's a good point.
Surely. It might be too bright, actually.
Yeah, I wonder.
Or it's too close to the sun because it'll be in a line.
You don't want to saturate all the instruments.
Well, you'll fry them.
Mm.
Okay, so that's not going to happen. Sorry to disappoint you. Sorry to excite you and then disappoint you. But that's probably not going to happen. I'm sure we'll get some beautiful shots though.
Yes, indeed. So yeah, Christy was talking all about how to study galaxies with the JWST, but she also mentioned briefly that you can study other things such as extrasolar planets, which just happen to need the same wavelength that these galaxy studies do. I think she mentioned that exoplanets weren't even discovered when JWST was conceived, and so that's another thing that is going to be a really cool science goal of JWST, is looking at planets going around other stars, like not the sun. And I do know that there is a bit of research happening in this area in parts of Africa. So if this is you, if you're involved in this, please get in touch. We would love to have a chat with you about your involvement with JWST.
I think we'll be seeing a lot of amazing research coming out of the JWST. We're going to have a huge amount of data, and I'm sure we'll have astronomers around the world working on it. And, with the SKA, Meerkat, and other telescopes coming along, I'm sure there's going to be a lot of complementary science coming out of Africa.
Absolutely. And I cannot wait to see the pictures that JWST will make. Even though it's at a longer wavelength to Hubble, we'll still be able to have these beautiful images, something similar to like what we saw coming out of Hubble. And I can see one of those pictures in the background in your calendar where you are there now, Dan. That must be a Hubble image, surely.
There you are. Spitzer.
Spitzer. Oh, okay.
Yeah.
That's a different space telescope. Yeah. Mm-hmm.
And yeah, so and I guess somebody like Jayan is probably itching to get hold of some of these,
yes.
because I'm sure they'll do the exact same thing as sort of make them human visible and interesting for us, but keeping all the physics.
Excellent. Alrighty. Thank you very much for listening, and we hope you'll join us again for another episode of The Cosmic Savannah.
As always, you can visit our website, thecosmicsavannah.com, where we'll have the transcript, links, pictures, and other stuff related to today's episode.
You can follow us on Twitter, Facebook, and Instagram at Cosmic Savannah. That's Savannah spelt Savannah.
Special thanks today to Professor Christy Tremonti for speaking with us.
Thanks to our social media manager, Sumari Hatting, and our audio editor, Jacob Fine.
Also to Mark Allnut for music production, Mihal Werchek for the photography, Carl Jones for astrophotography, and Susie Karras for graphic design.
We gratefully acknowledge support from the South African National Research Foundation, the South African Astronomical Observatory, and the University of Cape Town Astronomy Department.
You can subscribe on Apple Podcasts, Spotify, or wherever you get your podcasts, and we'd really appreciate it if you could rate and review us or recommend us to a friend.
And we'll speak to you next time on The Cosmic Savannah.